Welcome to the Machine Learning and Data Science track. First up this morning, we have Stephanie Wong on the need for serverless Python. Over to you, Stephanie.
Hi, everyone. I'm Stephanie, and I'm here to talk about the need for serverless Python. But first, just to introduce myself a bit, so I'm a PhD student at UC Berkeley, working on distributed systems, and I'm also a software engineer at a company called AnyScale, which is a startup that's focusing on making it simpler to develop and deploy distributed applications, specifically in the machine learning space. So finally, I'm also a lead committer for the open source Ray project, which I think is a key piece of serverless Python, and I'll talk more about that later. So in this talk, I'm going to cover the definition of serverless, at least the one we're going to use in this talk, and then the vision and requirements for a general purpose serverless platform. And finally, we'll talk about how I think Ray meets these requirements. So just to give a bit more background on Ray before we start, this is an open source framework for distributed Python that I and several others developed while at UC Berkeley, and we're continuing to develop the project at AnyScale. What Ray provides is a simple and universal API for building distributed applications, which I'll dive into more later in this talk. So we have a growing community, both in the research space and in the open source community. And we also have a growing ecosystem of libraries for everything from machine learning to reinforcement learning to data processing. So just to give some context for the Ray project and to explain what serverless is, it's useful to first look at how things are done today without serverless. So let's say I am a developer and I'm trying to build an application on my laptop, maybe just something to process my data set, which is all local. So I've got it all working now, and I want to use this thing that I hear such great things about to get better performance and scale. And that's, of course, the cloud. But how do I actually go about doing that? Well, it turns out that the cloud is not just a magical click of a button service. If I want to deploy a custom Python application, first I'll need to figure out what instances to use. And there's a bunch of possibilities here. So do I want a medium-sized machine or a large one? Do I need specialized hardware like persistent memory? Besides the instance type, I also need to figure out how many I should use, how to get more if I need them later, and where I should store my data. So clearly, figuring out these choices has little overlap with figuring out how to write a Python application. And getting these choices right could be really beneficial. I can get virtually unlimited resources and at low cost if I do it right. But if I get these wrong, I'll have to pay a lot in terms of either performance or cost. Now, larger companies with a DevOps team have the resources to navigate all of these challenges. But what if I'm just a single developer? So that brings us to the serverless vision. And serverless is really just another step towards the idealized picture I showed earlier, where a developer could just deploy her Python code to the cloud without having to think about how the deployment actually works. So you might be familiar with serverless in the context of function as a service, or FaaS, for example. Amazon Lambda provides an implementation of serverless functions for Python, among other languages. Now, FaaS is really about microservices taken to the extreme, where you're defining individual stateless functions that can be invoked over the network. And another key ingredient is that you get very high elasticity, so you can scale almost instantly. You don't need to worry about the scaling story for your application. So to see where FaaS fits in historically, we can look at how people have built and deployed applications over time. Originally, the only option was to deploy directly to bare metal servers, where you have to worry about all layers of the stack, from the hardware to the operating system. Now, with cloud computing, suddenly resources became widely available, but cloud providers needed some way to provide isolation for multiple tenants running on the same hardware. So then the main abstraction for applications became VMs. More recently, containers became the most popular way to deploy applications because they have much lower overhead and finer granularity than VMs. So no more worrying about the hardware and the operating system. And then finally today, we're starting to see serverless functions take off, where you're really just concerned with the code itself, the function definition that you want to deploy. The general trend that we just saw points to the two key benefits of serverless. First, the less developers have to think about deployment, the better. And even with containers, cloud users still have to think about how to deploy their code. With serverless, even this part goes away, and users just have to focus on developing the code itself. The second benefit is that with finer-grained units of computation, the cloud provider can offer highly elastic deployments. So compared to VMs, Lambda's users pay by the millisecond. And functions also have much fewer dependencies than containers or VMs, so they can be scaled up in a much shorter time. These benefits are true independent of the workload, even if we haven't yet realized them for general applications. So what is fast serverless used for today? Well, primarily it's used for defining functions that respond to web requests. More specifically, functions that are completely stateless. So if we think about a CRUD application where all of the important state is being stored in a database, this is a great fit for Lambdas because all of the updates can be issued from a completely stateless function. But despite the potential benefits of fast, many applications don't fit into the serverless paradigm. And the reason here is because these applications are stateful. So they have state held in a process that can't be easily moved to a database. And usually it's possible in principle to build these applications with stateless functions, but it becomes very inefficient. So what you really want is to be able to cache state in memory or on local SSD. And this kind of efficiency might not matter for basic web applications where all of your state is in a database, but it very much matters for applications such as machine learning, data processing, and other complex backend applications. So just to reiterate this point visually, for fast, you're basically applying a function to incoming requests independently. And so each function is independent of the other. But for applications like machine learning or data processing, these applications are very communication intensive and stateful. So they don't necessarily fit into this independent function pattern. So obviously, it's not a new observation that many applications are stateful. So the question is, where are the stateful serverless applications? Well, the market has produced plenty of these, and many of them predate the modern notion of serverless. In data processing, for example, we have services like Amazon Athena and Databricks that let users query and process data sets at a very high level without worrying about where the data lives or what resources are needed to execute the queries. Another vertical is machine learning, where you'll find many different services for training or inference. But one thing to note is that these stateful serverless apps are almost all custom built and they're proprietary services meant for a single vertical. So the main downsides of this are that developers get locked into a proprietary API, and that it takes a lot of glue to stitch together these different services to build an application. So in the next few slides, I want to show some evidence that I think shows that there's a community need for a more general serverless substrate. So the first is looking at the history of data processing on fast. If you remember, this is one of the complex applications that's non-trivial to write as stateless and independent functions. But people have tried, and there are a few projects that have attempted data processing on fast, specifically on AWS Lambda. Both of these projects generated lots of buzz, great looking benchmarks and academic papers, but neither was widely adopted in favor of more traditional data processing systems. And the main reason is that it's because of the current limitations of fast, which all have to do with keeping functions self-contained, independent, and stateless. So in some sense, this tells us that the desire for serverless is there, but the current fast offerings just aren't enough for certain applications. The second class of applications I want to look at are open source distributed ML libraries. And today there's actually an emerging ecosystem of ML libraries that integrate with the Ray project, including Claravaud for SGD and Hugging Face for NLP. Now, many of these libraries started as single node applications that used the open source Ray project to scale to multiple nodes, which was one of the original goals for the project. So why is this happening? Well, it turns out that there is a huge amount of effort to go distributed, which is of course a minimum bar to also make an application fully serverless. And in many cases, you might need a team of experts in distributed systems just to scale out a single node library. So our hope for Ray is for it to serve as an open source and a reliable distributed substrate for many different verticals. And so let's dig more into why we might want a general purpose serverless platform like Ray. So today, if you're building an application, you have the choice of narrow, specialized serverless solutions. So if your application happens to fit into the stateless pattern, that's great. Otherwise, if one of the existing proprietary vertical services works for you, you can also run serverlessly without too much effort. But for applications that don't fit into these molds, there's a really high barrier for building a serverless application. On the other hand, if we have a general purpose platform, vertical services can be implemented as libraries on top. So your application can either use these libraries directly, or it can build on the underlying platform itself, which supports both stateful and stateless computation patterns. And we all know that building an application today involves a lot of just gluing things together. So the other major benefit of a single general purpose platform is that you can mix and match distributed libraries with your own code. And so actually a good analogy here is with Python itself. Most of you writing scientific applications likely depend on libraries like NumPy instead of writing these low-level operations yourself. But you also often need Python to write custom logic or to stitch together operations from different libraries. And so the goal of having a single serverless platform is to allow that same kind of development to happen, but now with distributed Python and running in the cloud. So what are the challenges in building such a platform? And let's go back to the basic characteristics of serverless. We don't want users to have to worry about machines, and we want the system to be highly elastic. So to meet the requirements for a general purpose system, we also want universality, and that's to avoid the limitations of fast and be able to support stateful applications. We want composability to make it simple to stitch together different libraries in the same application, whereas in fast, you have all these, whereas in fast, you have all these independent functions that can't communicate with each other. And finally, portability to make applications runnable on any hardware and on any cloud. So generality doesn't come for free, and we have to make some trade-offs here. Compared to fast, one requirement that we could relax is the speed of elasticity. Many workloads out there don't necessarily need to scale up or down at a millisecond granularity. For example, it's often okay for a data science application to take a few minutes to scale up to thousands of CPUs. Even in an interactive application, a few seconds is okay. As an analogy, another place where we saw a similar trade-off was in databases. Traditional relational databases optimize for very fast queries, but are difficult to scale up. And in contrast, big data systems like Spark are often slower for common queries, but offer greater flexibility and scalability in terms of data size and distributed execution. So let's consider how well Ray meets these requirements. And you already saw some preview of this. The analogy I'm going to reiterate is that we're moving from many different special purpose systems for serverless to having one general purpose system for serverless. And this kind of shift has happened many times before. The most recent example is moving from relational databases to big data systems like Spark. And I think there's a similar analogy in moving from fast platforms to a system like Ray. So to contrast their APIs explicitly here, we can take a look at the different primitives offered. So with fast, we have functions, which is also a core primitive in Ray, where we have tasks, also known as remote functions. But Ray also offers actors for stateful computation, and you can think of these as kind of a remote version of a Python class. And Ray also explicitly allows tasks and actors to call each other, creating dependencies on the fly. So from a Python class, you can call a remote function, and that will get scheduled dynamically. For storage, FAST recommends reading and writing from cloud storage systems like S3, and Ray can of course do this too, but it also provides a distributed object store for fast in-memory execution, and it can also transparently transfer data between dependent functions that live on different nodes. Another more recent feature that we've been working on in the Ray object store is transparent spilling to remote storage, and that allows us to support out-of-core execution. Finally, FAST offers event-driven execution, such as through webhooks. And Ray can do the same through libraries like RayServe, which is built for web and machine learning model serving. But in addition to these, users can also program their own endpoints, and they can connect to other libraries that are more designed for offline computation, such as training. So let's also score these systems on the requirements that we outlined in the previous section. In terms of elasticity, I already mentioned that one of the things that we can potentially trade off is the speed of elasticity. So in FAST, you get very fine-grained auto-scaling at the granularity of a single function and at a millisecond level. In Ray, we can't quite match those scales, but we do have an application-aware autoscaler that can basically look at the resource demand on each node and add and remove nodes as needed. We can also perform node caching, and that essentially means keeping a warm pool of nodes to speed up scale up. In terms of not having to worry about machines, in FAST, the story here is pretty good. So you do have to choose from a number of container sizes, usually defined by the cloud provider. In Ray, you don't really have to think about nodes at all because the tasks and actors are actually specified with logical resources. So you can specify, for instance, a number of CPUs or an amount of memory that you require. In FAST, in terms of universality, I already talked quite a bit about how FAST currently only supports stateless functions. And so that means it's more meant for this web serving space. Whereas in Ray, we can support both stateless and stateful applications. And so that widens the scope to things like batch processing, model serving, where you have a large model in memory as part of your state, and other applications in machine learning. For composability, the story here is pretty bad in FAST because each function is assumed to be completely independent. So it's not really built for this. So if you want to say, call another function from a Lambda, you might have to do that by calling back to this external endpoint. In Ray, we can do this pretty easily because dependencies and nested tasks are actually explicitly part of the API. And we can also support very fast communication through the distributed memory layer in Ray. And finally, for portability, in FAST, of course, so far, this has been mainly an offering that's specific to different cloud providers. And Ray, the goal is to make it this open source distributed substrate. And so we wanted to be able to work on all of the popular operating systems on your laptop, Kubernetes, and any of the popular cloud providers. So in the future, we also have a lot more coming here. In terms of elasticity, we're mainly looking at improving the auto-scaling algorithms and our support for multi-tenancy. In terms of the ability to not have to worry about machines, one of the main things that we're looking at here is providing stronger fault tolerance guarantees. And then finally, in terms of generality, we want to improve the support for more data-intensive workloads. And you can ask me more about that later if you want. Okay, so I just want to give kind of a brief preview of some of the distributed libraries that are currently offered in Ray and some of the ones that we're currently working on. So here is kind of a breakdown of the current offerings, or at least the more popular ones on top of Ray. And so I've broken it up into machine learning training, machine learning serving, and data processing. So you can think of these as if you stitch together all of these different steps, you can actually build a completely end-to-end machine learning application. And so one of the beauties of Ray is that you can do all of this with a single platform. So on the machine learning training side, some of the earlier libraries were tuned for hyperparameter search and RLlib for reinforcement learning. And both of these were built directly on top of Ray. So at the time that they were developed, there was no existing single node library for these particular domains. And so some researchers at UC Berkeley actually built these libraries from scratch using Ray for distributed communication. More recently, we also have a collaboration with Horovod So we have Horovod on Ray. And there, basically, Horovod is using Ray as a method for orchestrating and coordinating the distributed processes in Horovod. And so Ray is basically acting as a distributed glue for this library. In the web serving and machine learning serving space, we have a new library called RayServe. And so this is a library that makes it simple to deploy a model. And so you can use RayServe to scale up your application, to upgrade to a different version of the model, and so on. On the data processing side, we have a number of libraries that are all ongoing development right now. So we have Modin, which you can think of as distributed pandas. We actually have a plugin for the library DAF, and so we call this DAF on Ray. And what this lets you do is actually execute any DAF DAG on top of Ray. So for example, you can have access to all of the DAF data frames API, but now executed on top of a Ray cluster. And so one of the benefits of that is that you can actually use DAF data frames with any of these other libraries very easily. And then finally, one of the libraries that we're really excited about most recently, and this is very much, you can keep an eye out for the release here, but this is known as datasets on Ray. And you can think of this as a distributed version of PyArrow. So what Ray is providing here is a way to distribute the data and the execution. And it's also acting as an in-memory storage layer for Arrow data. So some of the recent improvements that we've been working on here, as I mentioned earlier, are around transparent spilling to external storage, which allows out-of-core execution, and also optimizing the data transfer between nodes. So again, much like Python itself, the beauty of having a single platform for all of these libraries is that it allows you to pick one, none, or all of these libraries. And you can do that depending on the needs of your application. So what's next for Ray? Well, with our 1.0 release, we presented a general purpose API that's capable of supporting fully serverless applications in the future. But to realize this, we have to continue to grow the ecosystem of libraries, much like Python itself. And we have to tackle the remaining challenges and serverless execution, such as auto-scaling and fault tolerance. And actually, any skill is taking the lead on a lot of the challenges here. Future versions of Ray will also build on this goal. So in the open source project, we're also continuing our work on datasets in Ray, which we hope will provide a standard for passing and manipulating distributed datasets in Python, much like Apache Arrow did for single node data. We're also working on better auto-scaling and primitives for elastic applications. And if you're a library developer or someone who's just looking to scale their Python application, please get in touch with us over Slack or GitHub. Thanks, and I'll take any questions.
Hi. So let's all thank Stephanie. That was a great talk. And if you can just drop questions in the Q&A section, we can pick them out of there. Thank you. So first up, we have a question. Is there a the upvotes are changing everything in order. Is there a solution available for running Ray on an on-premise compute cluster?
Yeah, there is. So it's probably a bit more work to do that just because, so Ray, the open source project does come with a cluster launcher that works with any of the major cloud providers. But you can also just start Ray directly on your cluster. So depending on your exact environment, that might require a bit more work, but you can definitely do that today. And that's actually, I would say, a fairly common way of setting up Ray. And please talk to us if you do have trouble with that. Oh, sorry.
That's okay. Another question was, could you speak to the effort to take an app that I've got going on my desktop and porting it into Ray? What would that look like?
Yeah, so I think that really, this question is also kind of like saying, like, it depends like on the complexity of your Python application. So what Ray tries to do is make it very simple to go from just a standard Python program to a distributed version. And so I didn't actually show how you can do this, but the idea of tasks is basically a decorator that you can apply to a function. And then the idea of actors is a decorator that you can apply to a Python class. So in theory, actually, that should be like really simple. You just add these remote decorators to your code and then you're good to go. In reality, there might be more issues with that just because, distributed execution is not the same thing as local execution. It will cost a lot more to send data over the network. And there might be things, some like nuances like that are unexpected. So I think it depends on your application for sure. If you have something that's, embarrassingly parallel, that's going to be pretty simple. But if you have a more complex, say like a tree of tasks, that might get more complicated. Yeah.
And does Dask on Ray only work with Dask data frames, or does it also support Dask arrays and some of the other data structures in Dask?
Right. Yeah. So Dask on Ray actually works with any DAG in Dask. So it works also with Dask arrays. Yeah. Yeah, it's actually pretty cool. So the way that it works is the DAG of tasks. So, like functions and which dependencies there are between functions. That part is still built entirely in the Dask front end. But then the way that it gets executed is by submitting functions to array cluster. Yeah.
And we have one more question. What are some inexpensive or free computing instances that would be recommended for running Ray?
Yeah. So I'm not super sure about this question. I think that they were asking about, say, like instances on Amazon.
Yeah, I
Okay.
think so.
Yeah, if that's the question, I guess I would say that, you should go for something that's just like a CPU instance. And I would say like a rule of thumb is to like not go distributed unless you have to. So it's better to get, like one large machine that can like fit all of your applications. And there, like something like Ray can actually still help because what it provides is parallel execution then. And you can still use the Ray, even though it's not going to be distributed anymore. You can use the object store for shared memory, and that will basically improve the efficiency of communication between your processes. So I would say if it's possible, you should go for kind of the smallest single node instance that works for your application. And there again, this is like, again, the thing where it's difficult to say exactly like what parallelism your application needs. So you'd have to experiment a bit with that. And then if you do need to go distributed, it really depends on your application. So it's hard to say for sure there. Yeah, I guess one of the goals of this serverless idea is to try to make it so that like you don't actually have to think about this sort of stuff. So yeah, as you can see, there's like quite a bit of nuance here. Yeah.
All right. Thank you. And let's all thank Stephanie again. And thank you everyone for joining.
Yeah, thank you.